Dear students, Assalamu alaikum. In this brief chapter, we will have a very brief introduction into magnetostatic fields. Till now, we have only studied electrostatics. So, we will have a very brief discussion on magnetostatics. Okay. So, as I have told you earlier, electric field is due to primarily a static charge that creates. We normally visualize electric field as due to a charge. Okay. And magnetic field is due to a current, a moving charge. Okay. So we will first study this Biot-Savart's law. Okay. For example, we think about a particular wire, okay, through which current is flowing. I'm drawing this wire like this. Here you have a wire through which current I is flowing. Okay, I take a very small element of that wire of length L, dl. Okay, and I have a point here. Okay, I have a point here, point P, right? And I want to find out the magnetic field at this point due to the current element IDL. We have a current element, differential current element IDL. That's a you have differential current element IDL. Okay. So this is a differential current element, a vector. Okay. And you draw a vector R from that current element to the point P, right? So I want to find out what is the differential magnetic field, or else you want to see the elemental magnetic field DH at the point due to this current element. It's given by the Biot-Savart's law. It's given as the magnetic field, the elemental magnetic field at the point P due to the current element IDL is given as IDL cross product, okay, AR, okay, divided by 4 pi into magnitude of R square, right? So you know what is AR? AR is actually vector R divided by magnitude of vector R. It's the unit vector in the direction of R. So this is the Biot-Savart's law, using which you will be able to find out the magnetic field at any point. Okay. Now, you see, if this be the case, suppose if we want to find out the magnetic field due to the whole wire, what you have to do is you will have to simply integrate it over the whole length of that wire, right? Whole length of the wire L. You have to integrate it over the whole length of the wire L. Then you can get the total magnetic field as, okay, you can write the total magnetic field H equal to integral over the whole length of the wire L, then IDL cross AR divided by 4 pi into magnitude of R square. Understand? This is due to a line current. Line current, it is a current flowing through a line like this. Okay. Suppose if you have a surface current, okay, and through that surface current is flowing, okay. Suppose if you have a surface and through that surface current is flowing, you will actually represent the current in that surface by the surface current density K is the surface current density. Okay, and the unit of the surface current density is amperes per meter square, right? So in that case, for the surface current, you can write H equal to, okay, we have to do the integration over the whole surfaces, okay, the whole surface, yes. Then you have KdS, right, KdS cross AR divided by 4 pi R square. Similarly, if it be a case of a volume current, suppose if you have a volume like this, and the current is flowing through the whole volume like this, okay, and you have a volume current density given by J, okay, that is the volume current density, and the unit is amperes per meter cube. In that case, you can have H given as integral over the volume, then J dV cross AR divided by 4 pi R square. That is how you can extend the Biot-Savart's law for the case of the surface current as well as the volume current. Now, I will go and discuss what is the direction of this electric field, magnetic field intensity. For example, if the current is direction of H is given like this, so it's normally given by the right hand screw rule. For example, if the current is flowing like this, okay, the magnetic field will be in this direction. It will be going circular around it like this, okay, you go around it like this. So it's given by the right hand thumb rule. You know, this is the thumb, right, of the hand, and you have the fingers, right, you have the fingers coming like this, right, you have the fingers coming. So this is how you have the thumb rule, understand. So the magnetic field will be in the direction of the thumb fingers, and the current will be in the direction of the thumb, okay. That is how you have the direction for the thing, okay. Now we will see something else, like we will go into, suppose if I have a straight filamentary conductor like this, I have a point here P, right, and I have a straight filamentary conductor, okay, of length extending from this point to here, okay, the filamentary current conductor. There's a current I flowing through that conductor. This is a point A and this is the point B, right? What I do is from the I will take a very small length of that thing, and for example, I will draw a line like this. I will draw a line like this, okay, and I will extend this in the direction, and I will draw a perpendicular from the axial line passing through the filament, so that this angle will be 90 degree. This angle will be alpha 1. This angle will be alpha 2. Right. Now, I can find out the magnetic field at the point P is given by H equal to I by 2 pi, I by 4 pi rho cos alpha 2 minus cos alpha 1 A phi. Okay, where rho, this length is rho. That is how we will define the magnetic field for a straight filamentary conductor. Okay, for a straight filamentary conductor. You can say this is the magnetic field due to straight filamentary conductor. Okay, that's how we will find out the magnetic field due to a straight filamentary conductor. Now, suppose if the filamentary conductor is semi-infinite, that is something that is extending from this point to infinity. Okay, so you have the point here, right? In that case, you can say alpha 1 equal to 90 degree, right? And you have an alpha 2 here will be 0 degree, right? So if you substitute it into that equation, you will get H equal to I by 4 pi rho A phi. Okay, A phi. Understand? Now, if the conductor is infinite, that is, it is extending to infinity to minus infinity, you have a point here. Okay, here this is rho. So this angle will be 180 degree, that is alpha 1. Okay, it will be 180 degree, and you have alpha 2 will be equal to 0 degree. In that case, H will be having the value I by 2 pi rho infinite filamentary conductor. Okay. Now, if you take the case of A5, what is the direction of A5? A5 is given as the cross product of AL, that is this direction, right? And arrow is this direction. You have arrow in this direction, and you have AL in this direction. Thus, you will find out that A5. Okay. Now, we'll do a simple problem for this particular thing. For example, what I do is, I have the example. This is the x direction, a two-dimensional problem you have. Okay. And this is the y direction. I have a conductor like this. Zero, 1, 2, and this is conductor 1. This is conductor 2. Conductor 3. And the current of 10 ampere is flowing in the directions that is shown. Okay. Now, this is 1. Okay. And this is also 1. Now, we are asked to find out find H. You are asked to find H at the point question, right? So H is you are asked to find out the value H at 0, 0, 5. X is 0, Y is 0, and Z is 5, right? So this is X, this is the Y. Okay. So you have the side one in the X direction, right? This is X. This is X direction, and this is you have the X direction like this. You can draw the X direction like this, isn't it? You can draw the Z direction. You have the point 0, 0, 5 here, and this length, you know, rho equal to 5, right? And you know this is 1, 2 in this thing, right? So you will draw something like this, right? And current is flowing in this direction, so you can write this is alpha 1, right? So alpha 1 you can write just 90 degree, right? Alpha 1 equal to 90 degree. What about alpha 2? Alpha 2 is this angle, right? How to find out that angle? Okay, you can normally you know that the law is given like this: H equal to I by 4 pi rho cos alpha 2 minus cos alpha 1 A5. And you know, you can have, cos alpha 1, cos alpha 1 equal to cos 90 equal to 0, right? Cos alpha 2, it is adjacent side by hypotenuse, right? So it will be, adjacent side is 2 divided by hypotenuse is square root of 2 square plus 5 square, isn't it? So it is 2 by square root of 29, right? And rho equal to 5, isn't it? So you can write H equal to, the current is 10 ampere divided by 4 pi into 5 into 2 by square root of 29 minus 0 A5, right? So it will be minus 59.1 A5 milliamperes per meter. Now what is A5? You can find out A5 like this. Okay. A5, A5 equal to AL cross A rho, right? AL is in the x direction, right? So it is AX cross, right? And A rho is in the z direction, right? A rho is in the z direction. So it will be AX cross AZ equal to minus AY. So it will become minus 59.1 AY milliamperes per meter. That's the solution for this particular question. Okay. So that's the way how you will do the problem for this current element case. Right. I will introduce you to one more particular concept called Ampere's circuit law, and with that I will conclude this lecture. It gives the relation between the current and the magnetic field. Okay. Suppose if you have a closed path like this, right? you want to take the integral of some magnetic field H around this closed path. Okay, so this is a closed path L. So you have the integral given as H dot dl, where dl is a very differential length, right? So it will be equal to I enclosed. This is a statement of the Ampere circuit law. For example, if there is some current going through this, like this, and the magnetic field, okay, around the there is a path enclosing that current. For example, you have a path. This is the path. This is enclosing the current. You take the integral of the magnetic field around the closed path, then it will be equal to the current enclosed, right? This is something similar to the Gauss law that you have studied earlier in electrostatics, right? Where you have, instead of the current, you have the charge, and you find out the this thing around it. The magnetic flux is actually flux density is integrated over the surface which encloses that particular charge or charge distribution, whatever it is, right? From this, actually, you can get another law which is called del cross H equal to J. This is a Maxwell's equation. Okay. So where J, as you know, is the current surface. Okay. J is the surface current density. J is the surface current density. Amperes per meter square. So this is the statement of the Ampere's circuital law. Okay. Now we will give two examples of this particular circuit law. First example is infinite. Okay. Suppose along the z-axis. This is the z-axis. Along the z-axis, an infinitely long line current I is flowing through the z-axis. Okay. Infinitely long. Okay. Infinity. It's going to infinity. Okay. So we have a point here, P. Right. So what is the? We draw a perpendicular line with the length rho. Okay. So according to the Ampere's circuital law, you know, we can find out the relation, right? You know, I equal to integral h phi, right? A phi. Because the h is in the phi direction, right? Because it is going around the z-axis. Actually, the direction is A phi, right? Isn't it? And dot h dot, what is it? dl, right? dl, what is dl? H phi A phi is the direction of the magnetic field, and the differential length dl along that closed path, that circular closed path, is given by rho d phi, isn't it? And that direction is again A phi, isn't it? Clear? So you can take h phi, which is a constant outside, A phi and A phi, when you multiply, we will get it as one dot product, right? So if you do it like this, rho d phi is from 0 to 2 pi, isn't it? You have to find for the whole path, whole closed circular path around it. So you will get it as h5 into rho into 2 pi, isn't it? So that is I. So from that you can get h equal to I by 2 pi, right, rho a5. This law can be derived. Now we'll do one more example. Infinite sheet of current. You have, this is the y direction, this is the x direction, and this is the z direction. And I have an infinite sheet of current on the xy plane. I define an infinite sheet of current on the xy plane like this. Like this, and on that sheet of current you have a surface current flowing like this, right? And that surface current has a current density K, right? So you can write the surface current density K equal to, write it as Ky in the y direction. Okay. Now in this case you can find the magnetic field at any point above or below the plane like this. For example, if you have a point here, this is z greater than 0, right? And if you have a point here, z less than 0, right? For both these cases, I can write the equation for h as h equal to HO z less than 0, right? That is how you'll be able to write. So the same value of magnetic field intensity, but of opposite directions, above and below the plane. In general, you can write the formula for H in this case as, for this case you can write H equal to half of K cross AN, where N is the normal direction. You can say AN will be in this direction for a point upwards, and AN will be in this direction for a point which is below the plane, right? So in this particular case you have a AN equal to AZ. In this case it is AN equal to minus AZ. So it depends on the particular plane that you are using. Sometimes the plane may be the XZ plane, or sometimes it may be the YZ plane. Accordingly the thing will be changing. Okay. So that's all actually we will do about that thing. One small example we'll give, and that will stop. Okay. Example. You have two planes z equal to 0 and carry currents with the current density K equal to minus 10 AZ amperes per meter and amperes per meter square, and K equal to 10 this is AX 10 AX amperes per meter. Okay, determine HZ. HZ 111. Okay, so you have the Z equal to 0 plane, right? So that is XY plane itself, right? So you have the x-axis like this, y-axis like z-axis like this, and x-axis like this, and you have y-axis, and you have z-axis. You have a plane of z equal to 4, which is the plane on the xy plane itself, right? Okay, so you have a plane here and another plane, right? As z equal to 4. From if it is 4, you have a plane here, right? And the point is 111. 111 is having z value 1, right? So you have that point coming somewhere here, right? 111, z value is 1, right? So for the first plane, this is the z equal to 0 plane, and this is the z equal to 4 plane. For the first plane, you have an like this, right? For plane z equal to 0, you have an equal to az, right? And for plane z equal to 4, you have to draw the vector like this. Then you have an equal to minus az, right? Understand? So equation is half k, right? We have the equation half k cross a, right? So due to plane HZ equal to 0, Z equal to 0 equal to half k cross, that is k is, what is k? K is minus 10 AX cross AZ, isn't it? So how much is it? Minus half 10 AX cross, that is 5AY, right? 5AY. Similarly, for the second case, for H Z equal to 4, it is half of k is what value? K is 10AX cross minus AZ, right? Minus AZ. So it will be coming as half is 10 is 5, right? So I can write it as 5 AY. So what is the total? This thing total will be HZ equal to 0 plus HZ equal to 4 equal to 5 AY plus 5 AY equal to 10 AY amperes per meter. Okay. With this, I will conclude this particular lecture.